All right, good afternoon, everyone. My name is Austin Hickman. I'm a fifth-year PhD and a co-founder of Soctera. And what Soctera is doing is developing power amplifiers based on aluminum nitride that will enable next-generation performance and wireless communication systems. And so to begin, I'd like to show you this familiar image that you may have seen in a TV show or a movie. There's a blip on the radar. Something's out there, but the question is, what's out there? And this single dot of information can't tell you if it's a friend or foe or a truck or a plane. So to get that type of information, you need to move to much higher resolution radar systems. And that is on display in the shift here from this low resolution radar to millimeter wave. So to improve the resolution, you need to improve the frequency of your radar system. And so the higher the frequency, the more resolution, and we can obviously see a lot more about the object we're detecting. So we go from a dot to this, where we can not only tell what the object is, but we can tell the object's orientation or even the make and model of a vehicle. So improving the frequency of your radar system drastically improves the amount of information you're able to extract from the object you'd like to detect. And so one area in which this is very applicable is defense radar, which is trying to move to these millimeter wave technologies so that they can, detect more about what they're trying to see, whether it's missile defense or in the nose cone of a fighter jet. But the one limitation of moving to higher frequencies is that these signals don't travel as far. The higher the frequency, the more that the signal interacts with the surrounding environment. And because of that, you lose a lot of power as it travels through the air, and it dissipates before it can reach the desired target. And this issue is also shared in telecommunications. So a lot of you may have heard about the headaches of 5G rollout. And this is because as you move to higher frequencies, again, your signal begins to interact more. For telecommunications, the higher frequency allows users to download much faster, and they've been advertising download a movie in a couple seconds. So this is something they really want to push for, but of course, moving to these higher frequencies limits their range. And so it turns out that the millimeter wave revolution in both defense and commercial sectors is limited by the range. So how exactly can you improve the range? Well, the answer to that is quite simple. You increase the power of the signal. And when you increase the power via the power amplifier, which is kind of the last part of the radar system where this high frequency signal is fed in, and it's given a lot of power right before it's broadcast through the air. So if our goal is more range in millimeter wave, and we get that with more power, what limits the amount of power that we can provide to the signal? And the answer to that is materials. So the material with which the power amplifier is made. So now I'm going to show you just a couple of the materials that are commonly used to make power amplifiers today, and compare some of the key material factors that are relevant for making power amplifiers, those being high power, high temperature, and high speed. And so silicon here is of course very common because of how robust and mature it is, but for power amplifiers, it falls well short on this graph here. As you can see, the limits of its material only allows it to provide power up to a certain point well before the millimeter wave range. So now let's add a newer material, gallium nitride, which outperforms in all three phases, and as a result can provide high power up to much higher frequencies into the millimeter wave regime. And just to give you an idea, filling in this area on the plot, today that area in the plot is worth 750 million. So GaN really just came on the scene in the last 10 years in this application space, and it's projected to grow to over 2 billion within the next 5 years. So the question that we are trying to answer is, what material can enable true high power performance across the millimeter wave frequency range? And so the answer to that is aluminum nitride. And so we've plotted here with the other two materials, the material characteristics of aluminum nitride. And as you can see, aluminum nitride wins in both power and heat by far when compared to silicon and gallium nitride. And so what we've done at Soctera is kind of take the best of what each material, or of what aluminum nitride and gallium nitride have to offer, and incorporated them into this optimized structure. So using aluminum nitride as the heat sink and the top barrier, which limits your power. And then keeping this thin gallium nitride channel, which keeps the high speed performance of the device. And you can see the difference between our structure and what is conventionally used today. Yeah, better materials, just to take this back to customers, provides more power. We're projecting 2x the power, which ultimately increases the range for telecommunications and defense by 40%. So yeah, the team is comprised of myself and Reet, who is also a fifth-year PhD, and our advisors. And the reason we're able to lead this aluminum nitride revolution is because we have over 10 plus years of electronic grade aluminum nitride development, 3 patents filed on aluminum nitride electronics, and a lot of money has gone towards the development of this. And additionally, we've done customer discovery via the NSF I-Core and talked with people at Raytheon and Lockheed, as well as in telecommunications at Nokia and Ericsson, and discovered that this limited range really is a pain point in both industries. And just to wrap up, because I know I'm running out of time, I just want to leave you with this, that when the goal is millimeter wave range and you get that range with more power, that power is provided by materials, then the material necessary for the millimeter wave revolution is that provided by Soctera. And with that, I will stop and take a question.
Thanks, Austin. One question from the chat. Edward asked, and I'm just going to read it. Sending out an intense high frequency wave might be feasible in open spaces for defense or non-public communication, but won't it fry electronics if we start using them for other commercial purposes in an urban environment?
So yeah, I don't think at the frequencies we're talking about that it would actually fry electronics and the power levels. In a similar way that these high frequency signals are, actually where 5G is being implemented now, and the highest of frequencies and therefore high power is in urban environments. In city centers, because of the limited range, that's the only place that's really feasible right now, is places like New York City or LA. So as far as I'm aware right now, that's not an issue in terms of, interacting with other electronics to that degree, but that's something that I'll definitely need to become aware of if it is the case. So.